Right, so let's get started. Now, in the past, we discussed the controversy between Newton and Huygens. You guys remember that Newton was saying that light was more of particle type thing, and then Huygens was saying that it was more of waves. And in 1801, a physicist named Young conclusively demonstrated that light was in fact had possessed all the characteristics of waves. And in the early 20th century, the particle characteristics of light resurfaced again. And this is actually quite a mysterious and very fascinating duality between particle and wave, and them being both at the same time, particle and waves. And it's actually, this particular topic is quite beautifully merged and addressed in quantum mechanics. For those of you who are moving on in physics, you'll take that for sure. Some of you in chemistry might also take quantum mechanics. So you'll definitely see that later if you're in one of those two areas. Today we'll focus on the wave part of it. So previously we focused on the particles when we were looking at radiation pressure and so on. But today we'll look at the wave part of it. The hallmark characteristic for waves is that interference patterns can be produced when you have two sources which are simultaneously producing traveling waves at the exact same frequency. And we'll talk a lot about that today. So let's start off with that. So let's say I have two sources here, source 1 and source 2. Right? And these two sources, they're producing waves that are going out. They're, let's say, circular or spherical if you're thinking in three-dimensional. And same thing with this. And these two are both producing the same frequency, right? So same frequency. And if it's the same frequency, we know that has the same wavelength, right? Because we know that the relationship between frequency and wavelength is, well, frequency is equal to what? What is it? V over lambda or C over lambda, right? Is it C over lambda? Yes. So either C over lambda, since we're dealing with light, in this case it's C, but if you're dealing with sound, which is also possible, it'd be the speed of sound, which is around 240 meters per second. So if I take some point P over here, right? Again, this is going out in all directions. It's sort of like rings. And if a better way to think about it is if you take a pond and you throw a pebble in it or something, you can see the waves radiate outwards. And this is actually a nice problem for those in taking calculus, related rates. You guys always calculate the rate at which those circles are traveling out, right? That's really famous, not famous, but fun problem to do. So that's sort of the case you're looking at here. So it's possible that at point P, the two waves can arrive either in phase or completely out of phase or anywhere in between, depending on where that point P is. And by that I mean if the peaks arrive at the same time, I mean that, or the maximums arrive at the same time, I mean that the peaks from both of them arrive at the same time at that point, which means that if the peaks arrive at the same time, the minimums, the troughs, also arrive at the same time. So the mountains arrive at the same time, and the valleys also arrive at the same time. And as a result, at that point, because they arrive at the same point, the peaks become higher, and the valleys become lower. And we call this constructive interference, right? So those two are basically interfering with each other, and what you end up getting there is if these two peaks are arriving at the same time, then those two add up with respect to their respective amplitudes, and then give you a higher peak and a lower valley. Now, it's also possible, as I mentioned, that that they can arrive 180 degrees out of phase. So if it's 180 degrees out of phase, what's going to happen? The peaks of, let's say, the first one will arrive, and then the low, the valley, the troughs of the second one will arrive, which means that they'll both interfere. And when you add them both up, provided the amplitudes are both the same, of course, you'll get nothing. So this is called destructive interference. So if you look at a sine plot, sine or cosine doesn't matter, right? Something like that. This is over here pi, and this is going to be 2 pi, right? So this is for sine. Now, if I shift this plot by 90 degrees, basically, which means that let's say I'm starting it over here, I'll get something like this, which means that, yeah, they both have their zeros at the same time, but when this has a high, this has an absolute low, and when you add them both up, you'll get 0 throughout. So if they're off their phase by 180 degrees, then they interfere destructively, and they can completely erase each other, so to speak. And that's called destructive interference. And you can see this in 3 dimensions, or in 2 dimensions with water. When you look at a plane wave, or just the plane surface of water, you throw a pebble or some sort of something else, it'll generate rings and they go out. And if I have, so another interesting experiment to do is if I were to take tappers, you can have some sort of something that taps at a certain frequency. And when it taps at a certain frequency, you can, this thing, let's say this thing is tapping at a certain frequency, it provides waves at that frequency. If the second tapper is the same frequency, no phase difference, and they're both in phase, then you can see both of them add up, and then there are going to be points along when they'll both interfere destructively and provide that, and that's a 2-dimensional thing. In 3D, this thing happens with sound waves. Sound waves are more or less 3-dimensional. So when you're looking at sound again, like I said, they're waves, so they could interfere constructively, or they could interfere destructively, and so on. Same thing with electromagnetic radiation. Even those, like light and all that, those things are also 3-dimensional, so they could interfere constructively or destructively. One of my eccentric obsessions, if you will, has to do with high-fidelity sound systems and so on. So when I was an undergrad, my TA for my upper division thermodynamics stat-mech class, his advisor is actually quite a big shot. He did some work on like sonar and stuff back, a couple of decades ago or so. So he has this gigantic lab that they actually had a huge water tank and stuff where they had studied dolphins and sharks and so on with their sonar. But they built this sound isolation room. They called it silence room. So what they did was all the walls, they have cone-shaped foam in them. So basically you have something like this, zigzag all through the walls. So you have waves going in, and then they'll get muffled out through there, and nothing else comes out. So basically you go out there and let's say you say something, you're talking, you're going to have trouble hearing yourself because it's just everything gets damped out. So and this guy was actually a millionaire at that point. He before he came to grad school, he started some automation company, and then he got bought out by Oracle and made a few million off that. And so he and I also shared the same taste in hi-fi sound systems. So he brought a nice projector in. I brought my nice sound system that I can adjust the phase and all of the individual speakers. And we set it up in that sound room. And it was kind of difficult because even the floor was just mesh. So you didn't have anything reflecting off anything. So you had a mesh, and then below there you had, again, same zigzag, so it just was completely silent. So we used to mess around with these speakers, try to find the optimum position to sit while if you're in a theater or something like that. So everything else would get canceled out. And it was quite fun. I could just, let's say we're watching a movie, I just change the face just so that his part would get completely blocked out and he couldn't hear a thing. So good times. But yeah, sound again, so basically moral of the story is sound are waves, and you can have same type of interference patterns where you can have the peaks add up or the peak and troughs add up and give you destructive interference. So if we know that if particles oscillate, then their energy is proportional to their amplitude squared, right? So if I look at some energy of some oscillating charge, we know it's proportional to their amplitude. Let's say I'm looking at the electric field. It's proportional to the magnitude squared. Same thing with the magnetic field, but that doesn't really interfere. Since the energy must be conserved, as you go out farther out distance-wise, this thing, the energy has to fall off as if as proportional to 1 over the distance, or 1 over r. So the energy must be, or the amplitude of, let's say, a sound oscillation or whatever you're looking at, has to fall off as a function of 1 over the distance. And that has to do with conserving the surface area. And this only works with three-dimensional sound, electromagnetic, and so on. So this has to fall off as a rate of 1 over distance. If you look at the superposition of two waves, and in this case at some point p, and if you were to make the distance so large that r1 and r2 are much larger than the distance between those, if back here, if I'm looking at the case where let's say this is some distance r1, and this is some distance r2. So these two, r1 and r2, are so large compared to the distance between these two. Let's say the distance between these two is distance d. Then the amplitude difference between them, let's say these two have a slight amplitude difference between them, it doesn't matter anymore. So because it's quite small compared to those. So if there's any amplitude difference between those, in the case where r1 and r2 are much larger than d, then you can ignore the amplitude difference between them. So imagine if we're looking at, let me redraw this. So let's say I'm taking the same case as over there, and I have point 1, point 2. This is producing circular waves, or spherical waves, if you will, and I'm looking at some point p over there, just as I did back there, and I have some distance r1 and some distance r2 over here. Right? So let's say I'm going from path from point 2 to p. Now if that distance is half a wavelength larger than the distance between here and there, then this means that this wave will have to travel half a wavelength farther. And what will happen is the period of oscillation there will be larger than it is from point 1 to that point p we're looking at. And therefore, if it's half a wavelength larger, then we'll get something called destructive interference. So in order to go, let me, if I'm looking at r1 minus r2, so basically the difference between these two is about half a wavelength larger if it's plus or minus lambda over 2, or plus or minus 3/2 lambda, and so on, you'd get destructive interference. Right? And to get constructive interference, they can be off by a wavelength. So for constructive, sorry, this is supposed to be r2 minus r1. Actually, it doesn't matter because we're looking at the plus or minus of it anyways, but to stay consistent, r2 minus r1, this is going to be equal to, let's say it's n lambda here. So it can be off by one wavelength. And n can be anything from 0, plus or minus 1, plus or minus 2, and so on. So I can generalize this as well to some form of n. And I can say that r2 minus r1 is equal to 2n plus 1 times lambda over 2. And n can be 0, plus or minus 1, plus or minus 2, and so on. So over here, they're in phase, and over here, they're out of phase completely. So when they're out of phase, you'd get destructive interference. When they're in phase, you get constructive interference. Now, we looked at ellipses last time, right? And actually, I think I promised that I'd solve or derive the geometric optics equation using Fermat's principle, but we're sort of a bit short on time. This is more pressing, but on Friday I should have time, so I'll go through that on Friday. So we looked at ellipses on Friday, right? So we know that if I have 2 points, let's say 2 points like this, if the distance between those two, so to some point, like let's say r1 minus r2, if the sum of those two is a constant, then we got an ellipse last time, right? Now, if the difference between these two is a constant, then what would you get now? Does anyone know? Yes. So if r2 minus r1 over there, that's a constant, what do you get? You'd get hyperbolas in 2 dimensions. Now, if you generalize that to 3 dimensions, you'd get hyperboloids. Now, I came up with a little mathematical file for this again. This is just the form I'm writing in, and you can write this in actually many forms. But the goal here is to get a fraction over here, and basically all the substitutes have to, all the subsequent ones have to be odd on the numerator. So basically, I have lambda over 2 here. So everything else I want there to be an odd number to get the 1/2 factor. So 2n is always going to give me an even number. I add 1 to it, then I'll get an odd number all the time. All right, so here, wait, you guys can't see it. So here is a rendition of a hyperboloid. So hyperboloid is basically like two cones or 2 bowls, and you can see that. So you have bowls with space between them, and the space doesn't actually have to exist depending on how you define it. You can also have something like this. This would also count as a hyperboloid. So basically, it's hollow in the middle, and you get something like that. But when you think of hyperboloids as relative to actual hyperbola, this is what I'm talking about. So you can have something like this when you're looking at 3 dimensions, and in 2 dimensions you get something like this. Now remember, this r1, r2, so it's sort of like the focal points of this, and then let's say these 2 distances are r1. So the difference between these two is a constant, and I can move this around, and that always gives me a hyperbola. You can see the difference between them is always a constant here. Right, so I can move this, I can change both of them, and it'll give me still a hyperbola. So if I were to look at an ellipse, you can see this, it's a sum of the difference. So sum of the difference is always constant. I can change those 2 points around, and I'd still always get the sum of the distance as a constant there. And of course, if I vary this that distance, no, they would change the behavior of what my hyperbola would look like. All right, so that's good for now. Actually, since I'm already here, there. So remember I was talking about the waterways and all that. So this is something like that. So let's say I have the amplitudes of both the sources are the same, and they're oscillating at a certain frequency. Now, this is basically the distance between these two. I can change that, and you can see that the straight line there will either produce a maximum or a minimum. Now, let's say there's some random distance. I can change the phase here, and it's going to basically change whether at some point you have a maximum or a minimum. And they can go out. And you can sort of see the contour of this if I bring up the mesh. So you can see the sort of the contour plot of it. not so clearly, but anyways. And of course I can move, if I were to move this right on top of this, then I wouldn't have any difference in phase at all. Right? It's basically like one thing oscillating. I can just see the waves radiate outwards. The only time I'd get a difference is if there's actual interference between the waves. And you can see these lines over here, those nodes, they look like the hyperbolas, depending on what the axis and all that is. But right, so can you guys see that? So it sort of forms like a hyperbola here. So again, we can take something like this and get a hyperboloid. So you have these two surfaces. So if I was to have, like the waves radiating out like this, then if I were to rotate this axis, then you can sort of imagine a hyperboloid for this in 3 dimensions. So suppose I take a similar situation and I have 2 points that generate produce waves, and they have a separation of a distance d between them. Right? Now, immediately I can tell you, or you can tell me, that right in the middle, I'd get a line where it's always a maximum. So those two will interfere constructively at that point, right? Because that's basically where the distance between these two is the same. So there's no difference in the distance it has to travel, assuming these 2 points produce the same frequency, amplitude, and so on. Right in the middle, the distance between these two, so if it's the same situation over there, if I'm looking at P, R2 minus R1 is going to be equal to 0, right? Which means they're in phase according to that equation. N can be 0. When it's 0, they'd be in phase. So right away I can tell you this would give me a maximum there. Right? It would also give me a maximum, again, like something like over there, where I'd have R2 minus R1 is equal to lambda. And I'd have another one way over there, where R2 minus R1 is equal to, let's say, 2 lambda. And I can do the same thing on the other side, on the bottom. Now, that's all for the constructive ones. For the destructive ones, somewhere between lambda and this is where R1 minus R2 equals 0. So I'd have another line over here, something like that, where I'd get R2 minus R1 is equal to lambda over 2. So this, at that point, would interfere destructively. I get another one over here, R2 minus R1 equals 3/2 lambda. So this line, like I said, is always a maximum. And these points where I'm looking at the destructive interference, they're called nodal surfaces. And of course, points where they constructively interfere, you can call them antinodal surfaces also. So it's more or less the same thing. Now, if we were to rotate this around 3-dimensionally, you can see that it sort of form like a hyperboloid. You can see the bowl shape of this getting bigger. And this point right here, it would form a plane wave right there, where it's the maximum point. So we can have the same thing where we can also have R2 minus R1 is equal to lambda, 2 lambda, 3 lambda, and so on. Again, these will also be the maximums, not just this one. And as that shows over there in the surfaces where you have R2 minus R1 equals lambda over 2, 3/2 lambda, and so on, you'd get minimums or destructive. here, this would give you maximums. And if I were to put a screen on one of the sides, you'll actually be able to see the interference pattern. And hopefully I have time to show that today. If I were to put the screen there, so let's say, let me redraw a quick rough sketch of this. So again, I have my 2 points, distance d, and in the middle I have this. So this is lambda over 2. So this is lambda, and it goes on. If I have a screen over here, basically the distance between those two right here, this length will be lambda over 2 for between the constructive and destructive. So for the number of maximas based on this, we can say to get the number of maximums here, this is going to be equal to 2d over lambda. So depending on what the distance is here, I can get the number of maximums I have over there. This basically is the total distance between divided by whatever this difference is. Right, that'll give me the number of maximums. Yes, it is. Sorry. So to get more maxima, you can do a couple of things. You can either increase the distance between these two, or you can decrease the wavelength, or basically increase the frequency. Right? So to get more maximums, you can either increase the distance or increase the frequency, which means that you're decreasing the wavelength here. Now, it is essential for the frequencies of these 2 points to be the same. If they aren't the same, then they're not going to be in phase, and they don't have to be in phase, but if they aren't in phase, the position of maxima and the minima will change considerably. So let me put this down. There we go. So I mentioned hyperbolas a little bit ago. Let's take a quick look at what I mean by those. So let's take the same case where I have point 1, point 2, generating something. Now for hyperbolas, I'll have an asymptote like this, another asymptote like that, and the way the pattern would look like would be something like this, where I have this line approaching this asymptote, and same thing on the other side. It would approach that asymptote. So it approaches that line. I mean, you guys know this from high school math, right? Algebra 2, pre-cal, both of those went over hyperbolas and stuff. Now it approaches that line, so conceivably I can take whatever angle that line has, and the angle as seen from the source when you have the maxima or the minima. So if I'm looking at that angle from a certain distance away, I can get something like this. So same thing here, 2 points, distance d away. Let's take some line here. There's the middle point, some line there, middle point, some line there. So if I'm looking at R1 over here at some angle there, theta, and R2 is also some angle there, theta, and this is the middle point. Let's say I'm looking there. Now, if I were to look at what R1 minus or R2 minus R1 is, then I can simply draw a line down here, right? And basically this segment here, that's going to be my R2 minus R1. And I mean, you can also see by by a simple trick that this is also going to be theta there, right? If the distance were 0, then theta would be 0, and they'd be in phase and all that. So the distance to the angle here is theta, which means that I can express this as d sine theta. Now, to get constructive interference, I know that R2 minus R1 has to be equal to n lambda, right? And I'm saying that R2 minus R1 here is d sine theta. So, which means that sine theta, again, this theta is a function of n here, not function but as property of n here, is going to be n lambda over d. So this uniquely defines the whole slew of directions now. I can pick any angle there for any given n, and I can get a different set of maximas there. I can change the angle, I'll get a different set of maximas again. So this is for constructive. For destructive, we can do the same thing. We know for destructive, R2 minus R1 has to be 2n plus 1 lambda over 2, right? So I can say the same thing here. So I know that d sine theta n has to be equal to 2n plus 1 lambda over n, which means that from this, my angle, or sine of the angle, is going to be defined by 2n plus 1 lambda over 2d. Right? So this gives me constructive interference, and these angles over here give me destructive interference. So remember, I was telling you guys when I was messing with those high fidelity sound systems in that quiet room, I could position it so I could sit at a certain point where I get a maximum. I'd sit at another point where I can get a minimum. So if I had those sound system speakers here, everyone along where I have, so let's say these two are my speakers, right? They're producing a tone at some frequency. Right through the middle, anyone sitting along the middle will experience maximum. And from here, anyone sitting to a certain angle, let's say in theta and over here, would experience a minimum, would experience another maximum, and same thing over here. And anything in between would experience their range of minimums there, and so on. So the farther out you are, the more distance you have between the maximas and the minimas. Again, our department is sort of limited on these demonstrations, so I can't demonstrate that to you guys. But if you guys have speakers at home that you guys can produce a certain frequency through, it's not that difficult to reproduce this at all. So at home, I'm sure you guys have computer speakers, just 2 of them. Find some app on your iPhone or something to generate a certain tone, and then bob your head around at certain angles, and you can see at a certain angle you can have a maximum, certain angle you can have a minimum, and so on. So it's not that difficult to see that. Now, we love approximations here, so let's take an approximation here. So let's take the same thing we have over there, but I want to find the linear distance if I were to project onto a screen if it were really far away. So what I mean by that is I have the 2 points. Looking at it's supposed to be a straight line, but you get the picture. So I'm looking at it some distance far along distance L away, and I want to find out what the linear distance over here is. Let's say this is x. Now, on Friday we took approximations, right? Small angle approximations. We said that if the angle was really small, that sine of theta is going to be simply theta, cosine of theta is going to be 1, and then tangent of theta is going to be theta. And you guys know how this comes about, this approximation. So if I were to look at a plot of sine, right? Well, you know what? Let me just do it over here. Right, so I see my, or you guys see the sine plot over there, right? Yes, everyone see the sine plot? So now if I were to reduce the view I'm looking at, so for a smaller angle, let's say I'm looking at pi halves to pi halves. You can see it more or less flattens out a little bit. So you see that over here in this regime, basically looks like a flat line. So let's go even further. Let's say it's pi over 6. Pi over 6. See that basically looks like a flat line. And what this line essentially comes out to, in the middle at least, is something like this. And this function, the function of this is simply something similar to y equals x. So if I'm plotting tangent of or sine of theta for really small angles, it basically comes out to the one-to-one relationship here. So basically, whatever angle it is here, x and y are the same. So I'm just looking at the plot of x there. If I look at cosine, right? I mean, the smaller it is, like, if I'm looking at the small angle between something like that, you can just see it's a flat line over there for 1. So let's actually see that. Right, you can see that this is a plot of more or less 1, or y equals x. This more or less comes out to 1 over here for small angles. And we know that sine over cosine is tangent. So basically theta over 1 is simply theta. So this is the approximation for that for small angles. Does it make sense? Yes? All right. In physics, you'll see these approximations a lot. This, I'm sure you guys will learn about Taylor series, Maclaurin series, all the other series expansions. So expanding stuff, that is paramount. I mean, even if you expand this in Taylor series or something, sine of x, sine of theta is simply going to be theta plus blah, blah, theta over 2 factorial plus so on. Cosine will come out to 1 plus something or other. So we're taking that small approximation there. Anyways, so let's say this angle here is theta. Right? So what's going to happen now for small angles? My distance here, x over there, that's sine over this, right? So what I'd get here is x as a function of n is simply this length n lambda over d. Right? It boils down from what I had over here. Right? For constructive, basically this is what I'm looking at, the angle theta. That's n lambda over d. So I just plug in that n lambda over d and then multiplied by that L. Same thing applies for destructive interference. This is for constructive. And for destructive, I have xn equals L times 2n plus 1 lambda over 2d. Same thing as before, except my sine theta will just become theta here. That's it. So just look at that angle. And this is for destructive. And this is the constructive. So basically these lengths, those different lengths will tell me whether I'm looking at the constructive interference or whether I'm looking at destructive interference. So if I were to ask you to calculate X so and so amount of constructive interference, as you can basically, if it's really far away scenario, then you can use these to calculate that. If I'm telling you to calculate the so and so destructive nodes, then you can use this to calculate those distances. Now, if we have two sources with the same frequency, and we can tell where the maxima and minima will be, as well as predict the linear separation over there, then you know how far away you are from the sources, right? You can basically, if you know this separation and you know this distance, then you can figure out what this L is. Right? Stands to reason you can do that. Now, going back to our example of sound, by the way, one of the surveys, someone said that I don't do any demonstrations. I was puzzled by that, but I just know when I'm going to ask you guys not to leave after the break or until the end of class, because I'll do a demonstration. I'll make it worth your while. So, did you bring the cup? No? All right, I'll look at it during the break. But yeah, I'll do a demonstration for you guys. So let's look at sound waves again. And also another, actually more of a resounding issue was I don't do enough examples in class. That's true, but the way I mentioned in the beginning also, the way I wanted to structure this was that there's a lot of material to get through in class, a lot of information. So I'll get through all the theory behind it. I'll try to put in some numerical examples to give you an idea of a feel for things. But then during your recitations, that's when you can ask questions and go over example problems and so on. So there's no labs this week, so I'll ask the TAs to basically spend the whole time, so your recitation time and the lab times, going over any problems you have, practice problems, examples, and so on. So if you guys have the time to spend, it's going to be a good opportunity, especially if you ask for more examples, right? So again, take advantage of that. So back to this. Let's say, same thing. I have two loudspeakers over here. The distance between them, let's say, is equal to 1.5 meters away. So I have two speakers. I'm placing them 1.5 meters away. Now, what I would get here is, and I'm putting a frequency out of 3 kilohertz. And you guys can try this at home with your speakers and your iPhone, because there are tone apps. I used to annoy my friends with having really high-pitched tones and all that. So I'm sure there are apps there. So hook it up to your speakers, and if they're both the speakers, I'm sure they can only produce mono, so both the speakers will produce the same sound. You can reproduce the numbers here if you want. So if this is the frequency, then my wavelength is going to be whatever velocity over that frequency. And we know that the speed of sound is approximately 340 meters per second. And the frequency here, as I said, was 3,000 hertz, or 1/2 seconds, right? So the wavelength here is going to be 0.113 meters. So I can come up with different nodes or different antinodes for this. So if I have n over here and theta n over there, and I'm looking at the maximums for this one. So if I have n is 0, then my theta n is going to be 0. For n is 1, I'd get 4.3 degrees. For 2, I'd get 8.7 degrees. For n is 3, I'd get 13.1 degrees, and so on. For 10, I get approximately 49 degrees. And because we know, look, remember, sine of theta is approximately n lambda over d. Right, so I have everything I need there. I can calculate what the angles are from that. So if I were to have these two speakers 1.5 meters apart, right at 0, we have a maximum. Right? From here, from that point, if I were to deviate from the middle, angle 4.3 degrees, you'd have another maximum. And in the middle, of course, right in the middle, you'll have a complete minimum. And if I were to deviate 8.7 degrees from here, I'd get another maximum. 13.1, I'd get another maximum. 49 degrees, I'd get another maximum. And the same thing applies on the other side. So people in the back of the audience, it's in the middle somewhere, it's going to be really hard to basically hear anything between those two. And once you actually move about to get to the actual maximas, and you can hear the maximum amount. I mean, of course, it's not an ideal case that you'll have some, dampening and so on, things bouncing off the walls, the floor, seats, and so on. So it won't be perfect, but it's still a bloody good approximation. So you guys can do that. So I mean, if I were to look at this, so these two are what I'm looking at, the speakers, and let's say I'm looking at it some distance L away, then right through the middle I'd have a maximum, and over here at an angle of theta 1 I'd have x1 here, theta 2, and theta 3, and so on. So I can have points there. So if I were to calculate what those distances would be, where you would have to move, basically the distance between those nodes at a certain amount. So if I were to calculate the maximums for this, I can do that also. So let's say I'm looking at the length here in meters. And I'm looking at it 5 meters away, 10 meters away, and 15 meters away. So if I'm looking at 5 meters away, what I'd have here for this is going to be in centimeters here. I'd have for x1, I'd get 38 centimeters in the middle. For x2, I'd get 76. Sorry, for 10 meters away, and then for 15 meters away, I'd get 113 centimeters. For x2, I'd get 76, 152, 228, and so on. Actually, wait, is that right? Yeah, that's right. And in real life, things are not perfect, so I mean, those distances obviously wouldn't be exactly spot on, because as I said, you'd have a lot of reflection and other things to take into account. So it's more of a stochastic process here, but still we have a good approximation of what you can expect. Now, we said Young solved this discussion, and Young actually was a sound engineer as a trade. And as a sound engineer, he was very familiar with these interferences between sounds. And he knew that sound and sound can give you silence. And in 1801, he demonstrated convincingly that light and light can also create darkness. Now, before we go into Young's experiment, let's take a break. put your laptop, cell phones, all those away for 2 minutes, and take a piece of paper. And on that piece of paper, first write your name, then your section number. So what I did was I cut up the grapes, well, just basically in half, and I put it in the microwave. So now I'm going to turn it on, and pay close attention. I don't know if it's going to work, but I'm hoping it will. Everyone see that? No? Well, again, I'm sure everyone can smell it at this point. I'll try it a couple more, well, one more time. So 2 grapes in there. All right, that's good enough. So everyone saw that, right? Okay, so now write an explanation for what you think is happening on there. And I'll collect it right after. I'll give you guys a couple minutes to do that. And I'll give you guys up to 5 points extra credit on the final if you guys get it right. I mean, like I said, up to 5 points, but I mean, there's of course everything in the middle while I enjoy the remaining grape. What's that? Sure. If you guys can't come up with an explanation, write me a joke, and maybe if it's funny enough, I'll give you guys a couple of points. No, we were discussing Young, right? Young, he was a sound engineer, he knew a lot about the interference patterns, and he was able to deduce that sound and sound at some points produced silence. So, and therefore, he actually from there extrapolated that light and light at some points can produce darkness. And this was in fact the final nail in the coffin that would effectively demonstrate, at least at that point, uniquely in fact, that light in fact was waves. And this came as quite a bit of controversy between Huygens and Newton, because those two had opposing views on this. Now, the way Young proceeded with his experiment was as follows. If I can find my marker. Have you guys seen this before, that microwave thing? No? No? Like I said, the answer for that wasn't that trivial. I saw it recently, and basically my roommate and I had some amount of discussion. After that, I concluded that it had to be the dipole thing. All right, so the way he did this was he had a wall with basically 2 pinholes, small slits in there, and he had light coming in from here. Now you can think of the light here as plane waves coming in. So these plane waves are propagating in. Once they hit this little pinhole slits, they would create spherical or circular waves. Right? If you had a screen on the other side, you can see the interference pattern. Now these holes essentially act as Huygens sources. We discussed this last time, right? Every basically Huygens source at any point will produce its own waves from there. So these two act like Huygens sources, and you can then imagine spherical waves propagating out. Now we have the same exact situation with the sun, and you should have a certain angles theta where you should be able to see total darkness, and where you'll see other angles where you'll see total brightness. And let's demonstrate that with the lasers. So over here we have, I believe, a helium neon laser. Yeah, helium neon laser. So let's turn this around. All right. It's going to be really difficult to see because it's really small and down there. But I have one light, and what you have here, let me describe it actually before I turn it all off. So what I have here, if you want to think about it, I have basically a black box, not even a box, like a screen, a film, right? And over there we have really small slits. Let's say they're carved out by a razor or something. So it's really, really small in width. And then, but our laser is bigger than that. So what you'll see over there is an interference pattern that's caused by that. So depending on what the distance between those are, the width is, you can have different distances there. Does everyone see that? Yes? You can see one point laser produces, well, you have the maximum here, minimum, 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 and maximums on the other side. I should be able to change this. So this has finer distances, so you can see finer, smaller distances between those maxima and minima. And even smaller there, even finer. Can you guys see that? It's still quite discrete. Can't get anything out of there. Even over here, you can see fairly discrete points. You guys see that? You guys able to resolve that? So I mean, it's not just with these things. You can even take a strand of hair. Did you get one? Nope. Yes, I did get one. It's really thin. Oh. Lost it. There we go. It's a better one. All right. So a strand of hair. You guys see that? Right there. In the middle, it's really bright. On the sides, you can see essentially what is an interference pattern. Can anyone see it? Right, nothing here. As I bring it in, there. Right. So it's subtle, but it's still there. And they should be able to see something. We'll get to that also. All right. So that's how we essentially conducted his experiment, and we can actually figure out what those distances are. There it is. So I'm looking at the red laser. So the wavelength for this is about 6328 angstroms, right? And remember, 1 angstrom is 10 to the negative 10th, so it's negative 10th order of magnitude meters. And let's say the distance between well, that slit and what I'm looking at is about, well, it's about a couple of meters. So let's say it's about 1 meter, right? L is approximately 1 meter. So, and the diffraction grating, I know the slit, I looked it up, is D is approximately 0.088 millimeters. So from this, what I have here is in the middle I have a maximum at 0. I have a certain x1 that I get a maximum, certain x2 that I get a maximum, and then same thing over here, x1, x2. And based on this, I should be able to figure out what my theta is here and what my x1 is, and so on, x2, x3, and so on. So what's the relationship for this? Did I erase it? Anyone tell me what the relationship is between theta and L and all that? So sine of theta for maximum is equal to L. Well, what is it? Well, it's going to be n lambda over d, right? So this over here, x1 and so on, has to be approximately 7.2 centimeters. And theta from that is going to be 0.41 degrees. And from there, this is theta 1. And from there, you can calculate the other ones from that. Now, we looked at a well-defined frequency of light. Let's say we're looking at white light, something that's coming out of the sun or something that's coming out of these light bulbs. What's going to happen then? Well, we'll still be able to see these. Well, maybe, we'll see. So you have some x, and in the middle, 0, you get a maximum. Let's say we're looking at red and blue over here. Right, so I'm looking at my red and blue pens handy. So I'm looking at red and blue light. Now remember, this is a function of, well, if I'm looking at a farther distance away where I have to take L into account. So in this case, actually, I would have to take L into account, and I can ignore the angle there. But I'd get something to the effect of L lambda over D for my maximums and minimums, right? So for red, let's say this has a certain one over here, and that's L lambda over D. And then I'd get another one somewhere over here. Let's say it's 2L lambda over D, distance away. And same thing on the other side. For blue, my lambda is different, right? My wavelength for blue is smaller. So I wouldn't see it at the same place. I'd see it somewhere farther below. I'd see it somewhere over here. This is going to be my L. Oops. This is going to be my L lambda over D for the blue, and somewhere here is going to be 2L lambda over D for blue, and so on. So the distances, the lambdas are different. It's blue is smaller than red for the lambda, and so all these colors, everything in the spectrum, has its own separate maxima that doesn't have to do with anything else. So the maxima for red or the minima for red doesn't depend on blue, it doesn't depend on gray, it doesn't depend on any of their wavelengths. It has its own well-defined maximas and minimas. So they don't necessarily, well, they don't talk to each other at all for that. So, which is actually why I chose a well-defined frequency to show you guys that interference pattern. Now over here, I have a source of white light. Let's plug it in. So you guys can see the white light. Let's see if we plug in or put in front of that filter if I can see anything. Well, I don't see anything. But, actually I forgot about that. If you guys were to look at these, here I have a few, I'll pass them out. You guys take this and pass it around. Oh, actually it's kind of heavy, so just take them out. I don't have enough for the whole class, obviously, so you guys will have to share. Just take one, or you can pass them out. So I'm passing them out. Don't break them. And hold it up to that light, and you guys can see what sort of rainbow form. So like I said, I don't have enough for everyone, so you'll have to share. So just pass it around, and you guys should be able to see, well, sort of like a rainbow effect form where you have the lights forming different maximas and different minimas. Are you guys able to see that? This is a good opportunity to mention the notes. I'm working on them. They take a really long time. I'm near somewhere in the EM waves, working on the intensity and stuff. So I'm a couple lectures behind. But hopefully, my goal is to get caught up before the final. So you guys will have that weekend to look at it. But if they're not up, they're not up. Just look at the video lectures and get what you need out of them. Let me turn the lights completely off. About 8. That's what I'm thinking. 4 between midterm 3 and final. 2 between midterm 2 and midterm 3. And then 2 between midterm 0 and midterm 2. All right, everyone get a chance to see? So, yeah, turn the lights back on. All right, so please hand the slides back. And well, just pass them. Pass all the slides to your right. I'll get them from that. Thank you. Here. Ooh, a big stack. I'll take a few. Thank you. Thank you. Ooh, stack of them. Thank you. I got it. Do I have all of them? Do I have all the slides? All right, thank you. All right, so we can see the same thing for the light, or for the white light. So now what we did for light and sound so far, we can also do for radio waves, radar, microwave, and so on. So if I have, remember that transmitter I had that with the annoying tone? Let's say it was about 10 gigahertz, right? So it was about 10 gigahertz, which means that it was about, lambda was approximately 3 centimeters. So if I have that, I was modulating that at 1 kilohertz tone, right? And so if I'm looking at that, so I have the two loudspeakers there, or let's say I have two of those transmitters. And if I'm looking at from the middle, the distance is 23 centimeters. And if I'm looking at some theta here, theta 1 here for the maximum, if this is 0, x equals 0, and the distance between this and that is going to be 15.5 centimeters. And theta 1 for the maximum is going to be 7.5 degrees. And it's half of that for the minimums, for the silent part. So basically radar waves or microwaves can also kill themselves. So there's another idea I had. Maybe I can create something where I can sort of like the anti-police radar, but yeah, didn't work out. So now I'm looking at this with two transmitters, right? And we know we'll have a certain intensity at the maximums. What if I were to cover up one of those transmitters? Yeah, I know the angles and all that will change, but what's my intensity going to be? Is it going to be half? No. If you say it's half, then you probably don't have a good understanding of the intensity stuff and all that. It's actually going to be a fourth. Right? So think about that. Think about what the proportionality is between the electric fields and the intensity and all that. Because I may test you on the final on this and see if you guys actually understand this. Now, I guess we're out of time, so we'll look at interference intensities later. Yeah, we'll look at it tomorrow.